The next paper that we are going to have on this live stream is again about a composite material production process, and it is entitled Enhancing Fiber Length Measurements Performed by X-ray Computed Tomography for Improving the Production Quality of Composite Materials. It is authored by Filippo Zanini and Simone Carmignato from the University of Padua. Thanks for sending the presentation. We are looking forward to it.
Good morning, everybody. I am Filippo Zanini, postdoc researcher at the University of Padua in Italy. This work is entitled Enhancing Fiber Length Measurements Performed by X-ray Computed Tomography for Improving the Production Quality of Composite Materials, and it will be articulated in the following steps. I will start with an introduction on fiber-reinforced polymeric components produced via injection molding and on the possibilities related to the use of X-ray computed tomography to improve the quality of injection molding process and products. Then I will explain the objective of the work and the proposed experimental methodology. Finally, I will show the main outcomes and I will come to the conclusions. This work addresses the quality of polymers reinforced with glass fibers, which are composite materials increasingly used in industry to manufacture products with enhanced mechanical properties and lightweight. In particular, fiber-reinforced polymeric components are commonly fabricated using the injection molding process. It is known that the presence of long and well-oriented fibers is necessary to achieve good mechanical properties of the products, but the injection molding process itself often leads to relevant fiber breakage and complex fiber orientation. In particular, this research focuses on the fiber length that has a strong impact on performance of FRP components. The fiber's geometry is difficult to be properly acquired and analyzed because they are small inner features, invisible and inaccessible from the outside. In fact, the conventional method used to measure the fiber length is destructive and time-consuming, as it consists in the pyrolysis of the polymer matrix and in the fiber dispersion to enable optical measurements. In this context, X-ray computed tomography, that I will hereafter abbreviate in CT, is an advanced measuring technique that presents several advantages that will be discussed in the following. After the acquisition of a high number of bidimensional projections at different angular positions of the sample, a three-dimensional model can be reconstructed. This model can be used to perform non-contact and non-destructive analysis of outer as well as inner geometries, including microscale features. Moreover, metrological CT systems are currently available to perform accurate dimensional measurements. The acquisition of accurate three-dimensional models representing the geometry of actual workpieces and their characteristics, for example internal reinforcing fibers, is necessary to improve the quality of the manufacturing technology, in this case injection molding, and end products, in this case FRP components. Using the actual models instead of nominal models may allow improving process simulations and process modeling, which are enabling requirements for an Industry 4.0 vision. For example, injection molding simulations are commonly used to improve the part design and process parameters to enhance the final product's properties. A CT reconstructed model of an injection molded component will include information on the part geometry and on the internal characteristics such as fibers and porosity. In particular, the analysis of porosity, fiber concentration, and fiber orientation are commonly done using well-established procedures and algorithms, while the measurement of fiber length from CT data is more complicated. In fact, it is based on the segmentation of fibers from the polymer matrix and on the subsequent identification of single fibers to measure their length. These operations are difficult because of the various complex configurations assumed by the fibers after the injection molding process. For example, they can intersect or can be agglomerated in clusters. Despite these difficulties, there are already available software capable of measuring the fiber length from CT data. However, there is a lack of experimental methods to evaluate the accuracy of such measurements. For this reason, this work is aimed at proposing a new method to investigate the accuracy of CT fiber length measurements. The proposed approach is based on the substitution approach, according to which the information for determining the task-specific measurement uncertainty and correcting possible systematic errors can be derived from the difference between experimental measurement results and calibrated values. This approach can be applied when a calibrated object as much similar as possible to the actual workpieces is available with sufficiently low calibration uncertainty. According to the German guideline with the IVDE 2630 Part 2.1, the similarity conditions include material, size, geometry, measurement procedure, and environmental conditions. If these conditions are well respected, the same influences impact on both the calibrated sample and on workpieces to be actually tested. The application of the substitution approach to the measurement of fiber length is complicated by the fact that there are not reference objects available with calibrated fiber length. The principal reason is that the fibers are microfeatures not accessible from outside, hence a low uncertainty calibration performed using well-established measuring instruments, for example tactile or optical coordinate measuring systems, is not viable directly using actual FRP components. In order to implement the substitution approach, overcoming the difficulties related to the calibration task, a reference object was specifically designed and produced to satisfy the similarity with respect to actual FRP components and to allow the calibration of the length of a number of fibers using conventional techniques and with low uncertainty. The reference object was then measured with CT, and the measurement errors and the measurement uncertainty were determined by comparing the CT measured length of fibers with the calibrated values. The determined uncertainty can be associated to the fiber length measured on actual FRP workpieces. In particular, the reference object was conceived as an assembly of 4 subcomponents. The subcomponents A and B are both characterized by individual fibers arranged between 2 thin, transparent polymer layers. Subsample A contains straight fibers characterized by many different configurations, while subsample B only isolated fibers but both straight and curved. 2 separated samples were chosen for an easier fiber arrangement. The transparency of the polymeric layers enables fiber length calibration using an optical system, which needs the fibers to be visible from the outside and to lie on a plane orthogonal to the optical axis. Moreover, the transparent layers were chosen to have a material density similar to the matrix density of actual workpieces, for not influencing the setup of CT scanning parameters. Finally, 2 fiber reinforced polymeric layers cut out from an actual component, namely L1 and L2, surround some sample A and B in order to scan the reference object using the same CT scanning parameters used for the actual components. The object overall dimensions were chosen to scan the sample with the smallest voxel size of 3 microns achievable with the CT system used in this work. Subsamples A and B underwent optical calibration of the fiber length. In particular, a total of 41 fibers belonging to both subsample A and B were conducted by means of a coordinate measuring machine equipped with the imaging probing sensor. The 41 calibrated fibers have lengths ranging between about 0.076 mm and 4.2 mm and different configurations. A metrological CT system was used to scan the assembled reference object. In particular, 5 repeated scans of the object were conducted. The length of the calibrated fibers arranged in subsamples A and B was measured on the CT reconstructed models, and results were then compared with the corresponding calibrated values. Coming to the results, the diagram shows the deviations calculated as difference between the fiber lengths measured by CT and the corresponding calibrated values. The results are reported with the associated CT expanded measurement uncertainty, which was determined to be equal to 8.7 micrometers. The calibration uncertainty is reported in the diagram as well as a red area containing the reference red line. The maximum deviation is close to 9 micrometers, but most deviations are lower than 7 micrometers. The curved fibers show deviations comparable to those obtained for the straight fibers. This diagram shows the ratio between the measurement uncertainty and the measured length. It can be observed that the maximum ratio is slightly below 12% for the shortest measured fiber. It is also shown the ratio between the average systematic error, namely B, and the measured length, whose maximum is equal to 2.4% for the shortest measured fiber. Coming to the conclusions, this work proposed an experimental approach for verifying and enhancing the accuracy of fiber length measurements performed by means of X-ray computed tomography. This is important to establish CT as a tool to be effectively used for improving the quality of the injection molding process and final products. Accurate CT fiber measurements are also fundamental to provide experimental validation of injection molding process simulation and modeling in the Industry 4.0 context. The proposed approach consisted in performing repeated measurements of a reference object similar to the actual FRP workpieces in terms of material dimensions and geometry. Outcomes obtained with the specific scanning parameters used in this work showed that percentage deviations below 2.5% can be achieved for fiber lengths ranged between 0.076 mm and 4.2 mm, independently from the fiber shape. The measurement uncertainty was determined to be equal to 8.7 micrometers with maximum ratio U on L slightly below 12% for the shortest measured fiber. In this work, the fiber measurement was operated manually by the elaboration of CT data. Hence, future works will be focused on applying the proposed methodology to verify the accuracy of available software tools capable of measuring automatically the fiber length from CT data. In addition, the proposed approach can be easily extended to other composite materials. Thank you very much for your attention.
Thank you, Filippo Zanini, for sending that paper and that presentation. We're now switching live to the video call with Filippo Zanini. Filippo, hi, thanks for joining us in this session. Can you hear us?
Yes, I can hear you. Hi.
Thanks for sending that contribution.
Thank you.
The question that I wanted to discuss with you at first is about the deviation of the virtual model and the physical object. How much effort is that, and how is the method for that, and what is the relevance for the final uncertainty that you can achieve?
Okay, thank you for this question. I want to start by saying that actually a connection between our virtual models that we use, for example, for performing process simulation and for modeling the process, a connection between these virtual models with physical objects is very important. And it is also important that these models are actually accurately representative for the real object. So our effort is oriented to verifying the accuracy of our models and our measurements, and of course we want also to reduce this uncertainty in order to effectively help improving the process. In this case, we have some deviations which are actually very low. As I said in the conclusions, we obtained these deviations by performing manual measurements. on the
Yes.
fibers after the reconstruction of the model. Of course, there are also automatic tools that can do this, but in this case, the uncertainties can be higher, and we are going to test some of these tools soon with this reference object, which allows maybe also optimizing these tools to decrease the uncertainty.
Thank you. We're looking forward to that future publication of you. The second question for me revolves around the deviation that you have stated. You've stated a number like 2.5% of deviation. Can you relate this measurement deviation to the ultimate effect of that? So how does that relate to the strength of the structure, or how far are we away to know about that?
Well, yes, that's a good question as well. We are currently investigating this aspect. So now our focus was to proposing a method for verifying and maybe improving the accuracy of our CT measurements. The next step will be to, let's say, connect our results with, of course, ultimate testing, precise testing, to to find how these deviations can have an impact on, or can be correlated to these other tests.
Okay.
So future works will be done in this sense. Thank you.
Okay, thank you. So we have time for another question, and this question goes towards the automation of the measurement. So you were talking in the paper. You were talking about that the measurement could be automated, and there could be benefit for that. Can you describe on which benefits you think, in which situations would automation of this measurement be helpful?
Okay, maybe we should distinguish between automation of the measurement process, meaning the acquisition and reconstruction of a three-dimensional model, and the automation of the software part of the, let's say, measurement. Because, as I said in my previous answer, there are currently available tools allowing automated measurements of fibers starting from CT data, CT reconstructed model, and we are going to test them. Concerning the measurement itself, the scanning procedure, there are in the market systems that allows automation also for the measurement process, but for having very high accuracies and resolutions which are needed in this case for measuring the fibers, which are very small features. The automation could be some way difficult. So these measurements are still related to the user experience. So, of course, it is interesting to develop maybe some kind of automated measurement process, but we are still in the process to go there, let's say.
Thank you. Thanks for sharing these insights with us, these ideas. Thanks for joining the call. And yeah, we'll enjoy the song conference on. Thank you. Goodbye.
Thank you very much. Bye.
Thank you. So this was the presentation for the paper entitled Enhancing Fiber Length Measurements Performed by X-ray Computed Tomography for improving the production quality of composite materials, authored by Filippo Zanini and Simone Carmignato.